This is 5.6 properties of linear functions. The first question we have here is what patterns do we see in the table? Well, let's take a look here. If I look at the table, this goes up by 1. Here it goes up by 1, up by 1, up by 1, up by 1. This goes up by 0.75, and it actually goes up by like that the entire way down. So we see a consistent pattern. What if I wanted to write a rule for this pattern? Well, what if I wanted to say the cost relies on the number of toppings, and the number of toppings changes by 0.75, but a base price of $12. And we could prove that by plugging in any value on the table, and that'll work. So if we said C at 2, and that'll work all the way down, and we can test that on here, on the table, wherever. The patterns on the table are shown in the graph because it shows the same consistent increase, so this goes over by 1. And then it goes up by 0.75, so you can see that consistent step. And how can you tell from the table that the graph represents a linear relation? Because it goes up by a consistent increase for every single value. Here we have how to identify a linear relation. The cost for a car rental is $6 plus $20 for every 100 kilometers driven. The independent variable is the distance driven. The dependent variable is the cost. So if we're looking at a table of values, we can see that constant increase. This is the independent variable, the dependent variable. A constant change must occur in the dependent variable and in the independent variable. We can see it in a set of ordered pairs. We can see it works just like it does in the table. In the graph, we can see that the change is constant. And we can use each representation to calculate the rate of change. We also have this handy dandy little thing here that's going to remind us that this is the dependent variable, this is the rate of change, the independent variable, and the initial amount. And this will actually relate into the next chapter as well. So it is good to have on your mind as we go forward. Determining whether a table of values represents a linear relation. So if we check here, this goes up by 5 for each of these, and this one goes up by 9, 9, 9, 9. So this one is a linear relation. This one goes up by 5 each time. This one goes up by 75, and this one goes up by 225. So this one is not a relation. You don't have to check any farther. As soon as it no longer fits the pattern, it's gone. When graphing a linear, use a table of values to determine points on the graph. Label your axes, choose a scale. So this is the x-axis, this is the y-axis, always, always, always. Plug in -2, we get 31, 28, 25, 22, and 19. We will shrink our scale here. I'm going to put this as 5, 10, 15, 20, 30. Let's use, sure, this color. Why not? We have a point at -2. This guy will stay the same down here, so -2, 31. Ooh, that is not a good color to see. Let's try that again. Let's try this dark purple. Yeah, so we got -2 and 31, and we have -1 and 28, and we have 0 and 25, 1 and 22, and 2 and 19. So then if we get an arrow here, draw a line through them, reasonably straight. That would be our linear. Okay, next one. We can see that this is also linear too because it follows all of our rules. I'm going to lock this in place so it doesn't move on me again. We have 2x squared plus 5. So if I plug these in, I get 13, 7, 5, 7, 13. I'm going to make my scale go up by 2s. So this will be 1, 3, 5. No, it's literally just going up by 1s. Sorry, guys. So this will be 2, 4, 6, 8. Yeah, that looks right. So then my first point is -2, and 8, 10, 12. It's like right there. Then -1 and 7, 0 and 5. Here and here. And we connect those like this. This is very clearly not linear. And we can see that because we have values crossing over to the same spot. Y is equal to 5, so at all of these, y will equal 5. So 1, 2, 3, 4, 5. There. Get rid of that one. This guy is linear. He passes the vertical line test. Each value goes to where it's supposed to. And it may not be a function, but it's definitely a linear relation. And you can also tell that because it goes in a straight line. The other one, if we look up again, is not a linear relation because it is not a straight line. Linear has the word line in it. We are looking for things that are lines. Okay, x is equal to 1. This is another interesting one because this one is just completely a vertical line. So at x is equal to 1, we have a nice straight line here. So at any point on here, y could equal 0, -4, 6, 7, whatever, but x will always equal 1. Identifying a linear relation, a new car is purchased for $24,000 every year. The value of the car decreases. The value is related to time. So this should be time in years, value in dollars. So at year 0, the car is worth $24,000. Year 1, this goes down by 0.75. This changes to 20,400. So this goes down by 3,600, and that's because we went and we multiplied this by 0.75, and we subtracted how much it went down by, and we got this new value. Year 2, 17,340. So this went down by 30,060. So this is not linear. For a service call, an electrician charges $75 flat rate plus $50 for each hour he worked. The total cost for service is related to time. So time, H, cost, dollars. So at sub an hour, $75 flat rate. First hour, 75 plus 50, it gives us 125. Second hour, 150 plus, 75 plus 100 would give us 175. 3, we get 225, and we can see that this will consistently go up by 50, and this will consistently go up by 1. So this one is linear. Now we are going to determine the rate of change of a linear relation from its graph. A water tank on a farm near Swift Current, Saskatchewan holds 60,000 liters. Graph A represents the tank being filled, and graph B represents the tank being empty. So the independent variable that we are looking here is time, and the dependent is volume. Determine the rate of change of each relation to describe what it means. So if we are looking at the rate of change, you can use any two values on the same graph. So I'm going to use this one right here, and I'm going to use this one right here. So then rate of change, I have 4,000 minus 3,000. Because remember, rate of change is change in the dependent over change in the independent, or y2 minus y1 over x2 minus x1. 4,000 over 3,000, so at 4,000 liters, it's 80 minutes. At 3,000 liters, it is 60 minutes. So then that leaves us with 1,000 liters per minute for 20 minutes, sorry. Reduce that down, and that says 50 liters per minute. So for graph A, that says it will fill at a rate of 50 liters per minute. And for graph B, it'll be a little different. So if we look at graph B, we have a point at 6,000 liters, and that's at 0 minutes, minus 0 liters at 60 minutes. So then that becomes 6,000 over negative 60. So that reduces, this reduces, so that should be 1. So negative 100 liters per minute. So it goes down 100 liters per minute. So that means if it went down by 20, it should go down by 2,000. Yeah, perfect. So it will empty faster than it fills.